Well, good morning, everyone. I want to welcome you today to the latest WIRE's Advanced Technology webinar. Here with us today is Phipe Loose, who's a technical sales engineer with Enline. Enline operates in 30 countries across 5 continents, and their focus is on AI-powered energy solutions. And today, Phipe is here to talk to us about digitization of the grid through the use of digital twin. So he's going to explain all of that to us today. I'm really looking forward to it. For those of you who are watching, if you have any questions about the presentation as we go through, there's a question function over on the right-hand side of your screen. If you hit on that, you can type in your question. I'll collect those and I'll go through them with Phipe at the end of his presentation. But in the meantime, Phipe, welcome. Appreciate you doing this for WIRES. And interested to hear your presentation. So I'm going to go ahead and turn it over to you.
Thank you, Andrew. Thank you. And also thanks the audience for being present here. Thank you, Larry as well. The objective of this talk today is to give you a little bit more of the view that we inside Enline have for the upcoming future in terms of how this digitization of the grid may help, and of course will help the operators, people who are in the field controlling the grid. It's going to be an educational introduction, then I will pass through some of the products that Enline has, and I hopefully in the end I can show you the message that we are trying to bring to the world. Okay, so for a brief syllabus, I think it's important to start what is a digital twin. We will cover that. Later on, I will go and talk about Enline solutions, describing the path that we want to achieve in the future, and we will close with the main conclusions. Okay. So let's start some reasoning here. And I would like to start by addressing the philosophy on why engineers simulate things. So for the past 100 years, we have been working with computer systems, from calculators to supercomputers. And one of the main reasons in engineering for you to increase computing power is to drive more complex simulations. And why? Because engineering is a tool-driven science in which we rely on simulations in order to make some decision about designing a project or running a given construction, a given model. So in the philosophy of that, and trying now to, let's put ourselves into the chair of the operator, the engineer who's trying to work with these tools. A simulation is a static computer program in which the engineer has essentially at least 3 things, right? Some assumptions, and here we have an example in this slide. We have some assumptions, for example, in an electric circuit, if the circuit is lumped, if it's lossless, what are the fixed parameters? We have a program that describes the physics of a procedure, of a phenomenon, and then we have the initial conditions. And with that, the engineer configures the simulation and uses the outputs to design, manufacture, or operate process or systems. Okay, so let's have this in mind. And then what is the next level that we've been achieving with enough success over the decades is to bring that philosophy of simulation and now feed these simulations with data acquired in real time. So a digital twin, essentially, this is let's say the main standard that we have since 2010, where this was defined. Digital twins are data-driven models that are concatenated with physics and updated in real time. And perhaps the most common digital twin, let's say the most successful digital twin that we may have, that we had, was the Apollo 13. So you would see that this theory is theory that drives way back in the 50s, in the 60s with the NASA programs, where they configured a computer in land in Houston, and they drove lots of simulations based on the signals that were measured that were measured by the capsule in space. And you could say that this was one of the most successful digital twins we had. So in a nutshell, a digital twin is now this enhanced system. It's also a computer system that is receiving at the top of the simulation layer a data-driven layer that gathers data from multiple sources. So you would imagine, for instance, satellite data, data from sensors, from weather models, and from the machinery itself that you are simulating in the digital domain. And we call this taking data from the physical twin and feeding the digital twin. And in the digital twin, the goal here is to enhance your observability levels, because now with the physics and by controlling the physics carefully in the computer, you can establish, you can analyze variables and phenomena that you couldn't analyze with the physical twin, that would either rely on a significant amount of sensors, or it may even be unobservable in the real world. And that's the main goal of the digital twin, is to add this data-driven layer at the top of simulations to give you enhanced outputs. So you can make a decision with it. You can design a system. Now with this new, let's say this new, I would say, evolution of a simulation. So at Enline, we work with this assumption. We have products that create digital twins, and here are just some figures of some examples of what we are representing as digital twins. We have 3D models of transmission lines with vegetation. And the digital twin is not only this 3D view. It's important to emphasize that digital twin is the physics driven by data in a software that can be translated into a map view with alerts, or with a 3D environment, with a 3D environment. So it's important to emphasize, sometimes people they confuse digital twins as like 3D replicas. Of course, a 3D replica is a digital twin, but the digital twin is a much more broadened scope than having a replica in the 3D virtual world. So now, with this concept in our heads, let's look at the control room of the future, the place where operators in the electric power sector, they drive the decisions to maintain, control, and stabilize the system. And I would like to invite you with a metaphor, because when you talk about the power system, you are referring to the largest and most complex machine in the world. Every country has its huge own power system covering thousands of miles, and this all needs to be well synced. Otherwise, the structure collapses, as we just witnessed in Spain, in Portugal, and in France recently. And nowadays, I quote the past here, quote unquote, because it's still the present. It's like observing a dark room with a flashlight. So the room is dark, you have just one beam of light, you need to cover several aspects of the room. So you need to point this beam of light into several directions, losing visibility and trying to discover things with just this limited field. And by driving this, now putting ourselves into the chair of the operator, let's just try to open what are the tools for this dark room now the operator running the power system, what are the tools available today that most operators use to make decisions? So they have some sensors sensing some variables in the power system. If they have any, it's not, there aren't many countries working with, field sensors for the power system. So if there are very few. Lots of simulations. So remember, these files, I believe every operator engineer that I have known has a folder in its office machine with tons of files or cases, and they have to run these cases. They have to analyze by themselves these cases. They have to run multiple programs at once, and also rely on lots of documented manual documentation to make their decisions. So trying to create this environment, this logic of tools, of processes to drive a control room. I would say nowadays, also, of course, it's evolving with time. Depending on the country, it will be more well developed than others, but this is the broad perspective that we have nowadays. So now let's just look at the future. And by the future, I mean applying the philosophy of digital twin that I just described in order to create a brighter room. Let's say now that you want the power system to be as available as possible, all variables as available as possible for you. Kind of illuminate the room with digital tools. And here I would like to make an exercise, can be futurology, but we are not alone on this. What would be the tool set of this future, the yellow brick road, in order to sustain this new control room of the future? And here are some variables that we are not, and it's not only the vision of Enline, but the vision of many other players. For these power systems to behave as this brighter room that I just described, we would rely on only the necessary amount of sensors, not even sensors, and I'm not talking about sensoring transmission lines, I'm talking about sensoring in a general, broad scope, but only the necessary, because we don't want to flood the system with extra hardware in order to increase even more its costs and also its maintenance. So we will rely on field measurements. We would rely on a group of digital twins. So now imagine that, and I will present next. Now you have several digital twins for a particular power system. I'm not talking about only lines. I'm talking about transformers, substations, switchgears. Everything will be modeled with this data-driven layer at the top. And of course, unifying this entire amount of data into one single database, and preferably into one software that can manipulate all these things. And this is where we achieve what I call the dream tool set of the future, which is to have a tailored large language model that will consume this amount of data, that will have all the physics models embedded, and will assist the engineers, because now the data got so big that a human cannot even dive into it to make a decision. And that would be the yellow brick road, and that would be the dream for this control room, to have an AI sensing the system and assisting in decision making. But there's a path that we need to create. There's a path that we need to follow to achieve that. So now, talking about this path, I would like to dive deep into some of the tech we've been working here inside Enline as modules that will compose, as I said, this group of DTs that will be, in the end, manipulated by a large language model in a futuristic view of the control room. Not so futuristic, but. And one of them that we believe is going to be very important is the technology of dynamic line mapping. And this is very straightforward. It's been around for decades, but only now we've been having enough tech power to really apply it in the real world. And the goal here is to sense the weather via a thermal model, a tailored and sophisticated tailored model to assess transport capacity beyond the static ratings that we have in lines. So the goal here is to build a model, and we have built this model that controls the thermal balance of the heat between the conductor and the environment. And we leverage opportunity windows by sensing the weather, right, with our electrical models to either inject more power when it's needed or to control the injection of power now with a more holistic visibility, with a more complete view of a particular line or a set of lines. And the results that we've been witnessing by applying this model is an overall increment of 30% of capacity compared with static ratings, and the whole goal is to reduce future investment in infrastructure. Instead of building new lines, let's just work better with the lines that we have to achieve this more electrified future. Another component of this dynamic rating is another product of Enline we call Transient Admissible Transmissible Loading, or TATL. It's another way of building a digital twin with the heat model we developed. And the goal here is to turn this current control philosophy to temperature control and leverage the thermal constants we have in the transmission system to inject more power. Of course, controlling this injection under safety levels. And this would be the dynamic line rating with this assisted layer to control the transients. And it's another component we believe fundamental for the controlling of grids. With more emphasis in the stability of the grid once you have to achieve some overload situations. So just to summarize, and here I won't dive too much into this, I'm talking about products based on digital twins, and in this case, a model that assesses the dynamic exchange of heat across all spans of a transmission line or a grid, talking about overhead lines. And just to give you a summary of how we do inside Enline, we get a transmission line of a particular length. This is a 121 kilometer transmission line. And if I zoom in to check the spans and the towers here, I get information from geographical coordinates of each span and also the information of the infrastructure. And I compute this heat exchange model for each span, dividing it into subsegments, and compute this several times of the day. So you can imagine that we have a line. I chop this line into several subsegments, and then I run the model to each one of these segments. And we do this several times across the day, generating a massive amount of data for one transmission line to compute this dynamic exchange in order to leverage the weather. So the same thing we do with dynamic rating. And as I said before, we go from this current control to now temperature control because the model is able to sense several hot spots of a transmission line. Now imagine that we have a grid and we compute this same model for all lines of the grid several times across the day. Thousands and thousands of miles being driven by this model. Now comes the electrical part. We have just tackled the subject of the thermal capacity. In order to really give enough information for the operator, we need to be able now to go into the electrical realm in which the control of power, voltage, and current occur. And we need to create a digital twin of that particular part as well and connect these two recently created databases of process power, current, voltage, and temperature to work with the intelligence behind this control room of the future. So now I would like to show you another product we've been working with, which is our network state estimation. That is our way of constructing now the digital twin of a grid for its electrical behavior. And the goal here is to run a bunch of computer models focused mainly on power flows in order to see all possible cases of permissible voltages and currents that can happen into each node of a line. Now, as I've said in the other two products, we have the behavior of the thermal components. Now we're going to have the behavior of the electrical components. And of course, these two systems, they kind of talk to each other. They are coupled, right? And with these two technologies, I generate a massive amount of data for the control room of the future. I can work now with stability analysis, short circuit analysis, overloads, thermal overloads, and etc. And the way we do this with network state estimation, just to give you a brief example, this is a classic power system. If you are a power systems engineer, I believe you saw the same example in undergrad. If you have this simple system here, and the way our tech works is by assessing the nodes we can measure and try to estimate all the combinations of voltage, current, power on the nodes that we do not have any vision whatsoever due to lack of sensing equipment, for instance. Can we sense everything? Yes. It will be really costly and even costlier to maintain this under operation. So that's why we rely on estimations. And the way that we do in this electrical realm of the digital twin of the grid, let's say, we compute data, and these are some of the results we have of the output. And these are clouds of points, the likelihood of each voltage node and current that may happen across a power system with a probability analysis. What's the likelihood? And then you can see the clouds they spread. Every cloud that you are seeing here contains millions of points for just one particular bus. And the goal here is to turn this in raw data into information. Now comes the other part of the problem, which is I have the model, I have the data. How do I organize the data? And I give it in the form of a digestible way for the operator to work. And this is more or less how it works our network state estimation system. So now, remember, we have the DLR, we have the thermal behavior, now we have the electrical behavior. We digest this and we give this information in the form of dashboards to the operator. So they can really tackle the problem with a better enhanced view. Okay, I talked about an example that we see in the School of Engineering, but here, can you imagine how large the database would be for more complex systems? And this is just an example I took from one very well-written paper. The reference is written below. This is a 329 node system with distribution generation, unknown measurements whatsoever. So can you imagine how many clouds we would generate each moment the topology changes, each moment our sensing equipment changes, sense any changes in the behavior. So it's a huge amount of data only for the electrical part. We already covered the thermal data, the thermal part of the data. So what's the next step? What we do with this amount of data? How we digest this? And this is where I drive my main conclusions for this resilient future. We are nowadays walking towards a path of digitization. We are generating a lot of data, not only us in the power sector. There are other sectors that are already more advanced, the telecommunication sectors, image processing, and etc. And now we need to really walk towards this path of generating data and processing this data. And I believe that the power system nowadays is the perfect target for this AI revolution that we are seeing, because it's already a system that we've been simulating for decades now, because it's too large to really experiment on it. So we have a lot of experience in the models. Just now, we need to walk towards this path where we will add artificial intelligence to this data to make the system more resilient. So we believe that resilience will come with AI, with tailored AI. Here are just some of the examples of the actions we can do with AI. Recognize patterns in the operations, in the protection system that we have never recognized before. Estimate the entire system via sensorless model, because as I already said, you cannot censor everything. This is too costly to maintain. And also to help us in this decision of really what is the best control strategy for this large system. And just like we had in chess, where the systems, the computers are discovering new plays that were never played before, these will come with the operation of the power system as well. Once we add the AI layer into the real world problem for the control of the future. And we at Enline, we believe we are getting there, or at least we are in the right path. We are developing models. We are developing our AI component that is going to manipulate this entire system. And for the main conclusions, what we seek to develop in the upcoming years, or even in more optimistic situations in the upcoming, I don't know, 1 or 2 years, is to deploy an automated platform with artificial intelligence and tailored models to identify the patterns of operations across the system and put this inside the control room. And here is where I like to make a little joke. In the past, and this is a scene from Matrix where we see Morpheus walking, observing endless screens, and this was the future of 1999. This is not what we believe visibility is. Visibility is to reduce this matrix view, as I saw, these thousands of screens, to just the enough well-oriented screens and have the artificial intelligence handle the rest of the components, digesting only the information we require. And at Enline, our current status nowadays is in the development of these models. And I just showed you like 2 models, the thermal model of a digital grid, and also the electrical model, all talking to each other. I believe we are in this situation nowadays. And our yellow brick road for the future would be now to manipulate these models for a tailored grid and add this complex yet to be seen AI that will sense the weather, it will sense the thermal behavior of the grid, it will sense the electrical behavior of the grid, and will give valuable outputs for the operator. So I believe we are in this situation. Here is just a slide to show that there are more people believing in us. Some of our customers. Here we have inside our offices, we have a team of PhDs and masters, all working together to achieve this dream that we have. And frankly, to finish, I believe there's no turning back now from AI. When we start applying this concept that I just showed, and we are on the verge of applying this into the control room of the future to increase observability of the grid. So I would like to thank you all for your attention here. Larry, again, Andrew, thank you for the time, and I pass over to you guys for the questions. Thanks.
All right. Well, great. Thank you, Phipe. I just want to mention to people who are watching, if you do have any questions, please put them in the question function over on the right hand of your screen. I'll be happy to pass them along. I have a few questions I wanted to kind of tee up for you to tease out a little bit more. It's interesting. So if I get you right, it sounds like the matrix, I always thought that was supposed to be a vision of the future, but now you're saying it's a vision of the past, I guess, and we should leave it behind for the yellow brick road instead. Is that, did I get that right? I don't know. I may have mixed up some of the references there, but.
Yeah, the goal was like to joke a little bit about what people think of when you have when you think about having an enhanced visibility of something. Sometimes it's like multiple screens, several graphs, like people used to do with stocks in the past. Now it's just basically AI buying and selling stocks over and over. And I think we are in the power sector, we are still trying to digest this.
Yeah.
Just have enough screens, you know, and have this intelligence behind working with us.
Well, I wanted to follow up on a couple of points that you had in your slides just to get a little bit more clarification. I can't claim to have fully followed all of the aspects that you were going through. It seems pretty technically complex. One of the things you mentioned though was large language models, or LLMs. I'm not particularly conversant in that whole area, but can you talk a little bit in the long term about what the behavior of the LLM might be in the control room of the future as you were kind of laying it out there?
Yeah, this is an excellent question, because we are still experiencing how to operate with the large language models. And of course, I believe the interface today is the prompts that you have with ChatGPT, Gemini, right? Where you write something and they give you the output. I believe these LLMs in the control room will be much more oriented to giving alerts, but also with this prompt in mind. So you will be able to talk to this as much the same way we do with ChatGPT, but now with a tailored model inside. And it's not that we are going to give the access to the LLM to control our systems, but we will ask this tailored model how to better enhance the control system, the protection settings, and then the operator will give the final goal on the configuration. So I would imagine it would be something like that. Having the prompts that we already have established, some screens showing the outputs, and the reduced number of screens. I hope so, at least.
Well, thanks. The other question I had is, I'm assuming there's going to have to be some kind of deployment of new infrastructure to incorporate this type of new methodology. Can you talk a little bit about what, if I'm right, what kind of infrastructure would be involved in that type of a deployment?
Yeah, I think this is more an IT-oriented question, but I think we will see, and this is a topic that we are researching in power systems recently. There's digitized substations, digitized uh, servers, huge servers containing a lot of information and infrastructure to be able to really redirect this information to several other places. So I think we will have a communication infrastructure that will need to be deployed not only with the existing infrastructure that we already have, the protocols and etc., but it needs to be more. It needs to be whole service centered for the power system itself. So I think this is a challenge in the end. I'm not sure how we're going to follow, but the standardization of the sector is crucial to achieve this. And we shall see the power system much more like an IT-oriented system than it is nowadays. You know, with service, more like the internet. You see, an infrastructure like the internet.
Mm-hmm. I'm getting a couple of questions coming in, so let me turn over to those. One question that came in is, so who's the customer for this product? It sounds like it's applicable in the control room. So is that going to be the RTO here in the U.S., or is it going to be the individual transmission owner or transmission provider, or is it somebody else?
I think it can be both. Of course, the more impact you have in the decision of the system, the more complex your product should become. So TSOs, DSOs are great candidates for this. People who own transmission systems and are also prosumers, as we call, they produce their own energy. Everybody who has like a monitoring system to control the stability of a grid should be a nice customer for this future-oriented vision that we are presenting here.
Another question has to do with, are you aware of, or do you know of any type of incentives in the U.S. that might be applicable for this type of a system or program? And do you have any sense in terms of how it would work for purposes of cost recovery? Is this something that can be capitalized, or is it something that the utility itself would have to absorb?
In terms of like, I cannot say what are the main investors in the U.S., but it's becoming a trend worldwide to create these incentives, right? Here in Europe, we are already working with some European Union institutions to create these investments to increase the visibility of the grid. And in terms of cost recovery, I think it's complex, but it's like when you are deploying new technology, you need to be able to absorb the costs to see the profit in the future. But just like the way we did in the space program, for instance, or with the vaccines during COVID, someone needs to absorb this for the interest of the society, and then the profits will come later. My opinion on that.
Yeah. So I wanted to ask you, so we've seen some other technologies using AI for the energy market. Is there a difference between those types of uses of AI and what we've been talking about here?
It is. There is. the goal that the vision that we are trying, they can talk to each other, because the market, when you put the market into something, which is and I'm talking about the energy market, the goal is to control the system using the market signals, right? But we need to remember that the power system has its own infrastructure that needs to be monitored and taken care of. So the difference between this AI and ours is that we are more oriented to the health of the system rather than, this control via markets. Sometimes the control via markets they are very effective into balancing the system, but only the price signals they are not enough to guarantee a stability and a more oriented system for the penetration of renewables, for controlling this unstable loads we've been sensing over the decades and so on. So in a nutshell, we are more oriented to the health of the system with our models rather than, achieving the market. Of course, we are messing with the market as well with our technologies, but these two products are more oriented to this point of stability.
I've got another question that came in that's also focused on AI, and I'm gonna have to read part of this to you. So,
Okay.
The main advantage of AI is the ability to find patterns and provide insights in a very short fraction of time. How do you address the lack of trust on AI outputs? And do you see any utility trusting AI to take action rather than waiting for a human to validate?
Mm-hmm. Mm-hmm. Yeah, that's a tricky and wonderful question. So I believe there's a trend nowadays in artificial intelligence, which are called the PINs, physical inferred neural networks. And what they're trying to do is basically create these neural networks that are driven by mathematical laws that describes the physics of the world. And then you penalize the network and you try to it's not forcing, but you orient the reasoning of the network towards a physics-oriented model. In order to really, let's say, fight against these AI illusions, right, hallucinations, I think that's the goal. We need to run more of these models and investigate more into this. And what was the last question, Larry? Sorry.
It just said, how do you see a utility trusting AI enough to take action rather than waiting for a human to validate? In other words, just going forward based on, I guess, on the what they're getting from AI rather than doing the human double checking process on that, I think is what they're driving at.
Yeah. So great. Yeah. I think the same process they did when they started to run power flows in simulations. They need to experiment on that, unfortunately, at least in my opinion. They need to work with some experimentation. Also, another component would be reinforcement learning. It's not that we're going to completely abandon the old procedures, and that's another interesting bridge. These new tailored models should be able to talk with the old procedures, so you could reinforce the best practices. But experimentation, working towards the same path they worked when they started to automate some things like power flows and other types of controls.
Great. Well, can you, and then I have just another one I wanted to do, which is, can you talk a little bit about some of the successful examples where you've had been deploying this type of technology, whether that's over in Europe or somewhere else, or somewhere here in the US, just to get an idea of where you've had some experience successfully moving forward with it. And what were some of the, I guess also what were some of the lessons learned from those efforts?
Yeah, we are having a nice penetration in South America, especially with the network state estimator. We're still working with some customers on that, on the phase of deploying the module of the network state estimator. Also in Europe, we have other clients who are working with the thermal model and with this dynamic view of the grid by changing this current control philosophy to temperature control now by sensing it. And regarding the lessons learned, you tackled an interesting approach in the last question. There's a conservative view when you operate power systems, and one of the lessons that we are observing is to how we adapt this technology to the workflow of the operators. Because the workflow of someone who is in the US may be different from the workflow of someone in Europe, even in Spain or France, depending on the nature of the power system, the workflows are different. And we understand that there's gotta be some standardization how to deploy this. We are working on it, but we're still trying to figure it out. And these are the most valuable lessons, in my opinion. When we work with the customer and the customer says, look, this is great, but it doesn't work for me that way. Can you please tailor it? And through baby steps, we are achieving that.
Great. Well, Phipe, I want to thank you and Enline for doing the presentation. This is really interesting to see where we may be headed in the future. I know you've got your contact information here. We will, for everyone watching, we will post this presentation on our website. So if there was anything to follow up on, you can circle back to it and get the contact information there. Really appreciate your taking the time to do this. Thanks everybody for tuning in on this. Those are some great questions that came in, better than I could have thought of, for sure. So I think it was great that we had an opportunity to flesh some of it out through the questions from folks watching the presentation. So,
thank you, Larry. Thank you, Andrew, for this opportunity. And also, again, thanks the audience for the questions.
All right, great. Well, thank you very much. And that's the end of this webinar presentation. So thanks everybody who had tuned in.
Thank you. Bye. Bye.